All right, we'll see. My computer's behaving a little funny today, so I hope it works out. Okay, so today we are covering chapter 5, and this is probability. Okay, and so when we talk about probability is the big idea here is we're trying to express how likely or unlikely an event is. Okay, so with probability, and so, you know, the probability is used only for uncertain events. Okay, so we use describe the kind of the chance of an uncertain event. Okay, so we don't use it for describing things that are known, are factual. Okay, we don't say, what is the probability that yesterday was April 23rd? That there's no probability there. It's just a fact. Okay, so we only talk about things that have uncertainty. And we might have some event A. Okay, and then we say the probability that A happens is the probability of A, can also be written just P of A. Okay, this is the probability of A. And thus, we can talk about, we will flip a coin and we can ask, what is the probability the coin lands heads? Okay. And so we would say this thing that we're talking about is the probability of heads. And we would say this probability is equal to what? What is this equal to? 1/2 or 0.5. Okay. And so this number 0.5, for here we are using the frequentist or classical view of probability. Okay, so in our course, frequentist or classical view of probability, as opposed to in other courses you might hear about the Bayesian view of probability. Okay, we're not gonna cover the Bayesian view of probability in this course. We're sticking to the frequentist or classical view of probability. And the idea behind the frequentist or classical view of probability is that this number 0.5 represents the long-run relative frequency of that event. So the probability of an event is the long-run relative frequency of the event. Okay, so what do we mean by the long run relative frequency? Well, if I flip the coin 10 times, it could land heads 5 times out of 10, and here we get this number 0.5. So, you know. Okay. I could get, you know, 5 heads out of 10. And in that case, my relative frequency would be 5 out of 10 or 0.5. Okay? That's fine. My relative frequency after 10 flips, if I have 5 heads, is 0.5. Okay? It's also possible that my relative frequency is equal to 0.3. That's if I get 3 heads out of 10. Okay? Or I could also get, you know, 0.6, 6 heads out of 10. Okay, those are all within the realm of possibility. I mean, it's even possible for me to get 10 heads out of 10 flips, although that's pretty unlikely. Okay, but you know, these other outcomes, 5 out of 10, 6 out of 10, 3 out of 10, those seem reasonably likely. And so our relative frequency here, you know, has a bit of variation. The idea here is this is where the long run part comes in, is that in the long run, however, okay, if I flip the coin millions of times, so in the long run meaning approaching infinity, so not possible in real life, but in the long run, the relative frequency you know, heads divided by total flips will approach 1/2. Okay. And so that's kind of what we mean by when we talk about probabilities. We're talking about the long run relative frequency. Okay, so when we say probability that the coin lands heads equals 0.5, that means in the long run, so in the long run, the relative frequency approaches 0.5. So if I flip the coin 100,000 times, you know, I might have 50,000 heads plus or minus, you know, 100 or so. But in that case, my relative frequency will be something like 0.501 or 0.499, and a lot closer to that actual value of 0.5. So we've seen, so far we've kind of talked about there are two types of probability. Okay, and one is the theoretic probability. And this is, you know, this is going to kind of be the focus of our chapter. So, focus of our probability chapter. And these are probabilities calculated from mathematical rules. Probability is calculated theoretic probability calculated for mathematical rules, right? And so, the example here would be a coin has two sides. Okay. When we flip a coin, both sides are equally likely. Okay, therefore, the coin will land heads with probability equal to 1/2 or 0.5. That's a theoretic probability. And we'll learn more rules today and, Wednesday and next week. So we're starting our chapter on probability here, okay? So the coin will land heads with probability 1/2 because both sides are equally likely. So that's a theoretic probability. The other type of probability is the empirical probability. Empirical probability, as the name might suggest, is we can think of it as an estimate of the probability by using evidence. Okay, or in this case, actual, so the relative frequency from actual trials, or actual trials or simulations of trials. Okay, so a silly example is, let's say you are an alien from another planet, okay? You have never seen a coin before in your life. And you have no idea how a coin works, okay? Coin before in your life. You have no idea how coin flips work. And your alien overlord says, I want to know the probability the coin lands heads. So at this point, you have no notion that both sides are equally likely. For all you know is that when you flip a coin, anything could happen, okay? It could always land heads, we don't really know, okay? So, but, we still want to know the probability that the coin lands heads. Okay, so what we do is we just start flipping the coin and see what happens, okay? So, so we just do some experiments. In this case, we flip the coin. Okay, so let's say we flip it 100 times. And it lands heads. "47 times. Okay, the coin flip lands heads 47 times. Therefore, my empirical probability is just this relative frequency. Which would be 47 divided by 100, okay, or 0.47. And so in this case, what we report back is we say, based on my evidence, my relative frequency is 0.47. Therefore, in the future, if I flip the coin again, I expect it to land heads with a probability close to 0.47. Heads with a probability close to 0.47. Okay, and that's what we do. This empirical probability is very useful in situations where we don't understand either the physics or the mechanism, or we don't have a formula to just plug in information and get a result. Okay, so empirical probability sometimes when formulas do not exist. All right, so this happens quite a bit during election seasons. They'll say somebody might want to do a study, and they might want to go, okay, what is the probability that if somebody is female, is this age, has a college degree, is of this race, what is the probability that this person will vote for this candidate? Okay. Now there's no formula that exists that just says, oh, plug in the person's gender, plug in the person's age, plug in the person's ethnicity and I don't know, whatever, educational status. Okay. What we do is we go out and gather data, and we say, okay, well, we surveyed 1,000 other people that fit this profile. Okay. Out of the 1,000 people that fit this profile, 72% will support this candidate, and 20-something% will support the other candidate. Therefore, if we meet another person that fits these profile traits, our best guess is that this person has a 72% probability of voting for candidate A. Okay? So that's all empirical probability. We don't have, there's no formula that exists that you can plug this stuff in. Okay. So here these would be, kind of probabilities. So examples, probabilities based on survey results. Okay, we're using the survey results, the actual outcomes, to estimate a probability. We don't have it. Another example would be a lot of times you have simulations. So right now it's the NBA playoffs, but any sporting event, okay, you go to Las Vegas and they have the sports book where they have odds and they have probabilities for we think this team is going to win with this probability, something like that. You can place bets. How are they estimating these things? Okay, well, every system is different. Every place is different, but some places use simulations, and they might, some of the simulations have gotten quite good, and so you can imagine having a computer play a game against itself. Okay, and so in the computer, you might be able to put in information about each team, and use that to simulate the outcome of a game. And maybe you simulate 1,000 games, and in 1,000 games, Team A wins 62% of the time. Okay, therefore, the probability, your guess of the actual probability, is going to be 62%. That Team A will win. Okay. Of course, that's going to depend on how good your simulation is, but the fact that you're not just plugging numbers into a formula, but rather you are running simulations, that makes it an empirical probability. Okay, so these would be probabilities based on simulations. Okay, so probably, so, political election predictions. Or based on simulations, this will be, kind of sporting event outcomes. So this is empirical probability. It's very useful, especially when the systems are complex and we don't have mathematical models for everything. You can take, if you're interested in this kind of stuff, you can take courses on kind of computer simulation methods, which is an effective way to estimate probabilities. But that's beyond the scope of our course. Okay, so this is about all I'm going to say about empirical probability. You should know that it exists and kind of some of the situations where it might be used. But the rest of our time in probability will be focused on theoretic probabilities. Okay, so as far as theoretic probabilities go, we might say we have some event A. Okay, and thus the probability that A occurs is P of A, okay? This is a number. The probability of an event, that's a number. A is not a number. A is an event. It is not a number. Okay, so we can say the probability the coin lands heads is 0.5, but it is not correct to say heads is equal to 0.5. Okay, it's the probability the coin lands heads that is equal to 0.5. The probability for any event, probability of A is always between 0 and 1. Okay, if the probability of the event is equal to 0, then A is impossible, or A will never happen. If the probability of A is equal to 1, A is certain. It always happens. And then we say we have something called the complement of A. Complement here is spelled with an E. Complement of A is the event that A does not happen. Okay, so we write the complement of A as A complement or not A. Okay. And the probability of the complement of A, this is equal to 1 minus the probability of A. Or put another way, the probability of A plus the probability of its complement is equal to 1. Okay? Meaning that A together with its complement forms the entire universe of what can happen. Right? So whatever you think of in life, there's only two possibilities. Either it is or it is not. Okay, so okay, either something will happen in your lifetime or that will not happen in your lifetime. There's no other possibility. Okay, A and its complement together, they make the entire universe being one. Okay, let's talk about some of these rules. All right, we have 4 situations, okay? Rules for 4 situations. Okay, so let's say we have 2 events, A and B. Okay, the probability of A or B, this is the probability that A and or B occurs. Okay, so whenever you see or in probability and statistics, in probability, or is always an inclusive or, meaning and or. Because in the English language, we have a little bit of ambiguity about the word or. A lot of times we use the word or exclusively. So for example, I can ask you this question. Do you like chocolate or vanilla ice cream? And your answer to that question would be what? I like chocolate ice cream. Or you might say, I like vanilla ice cream or something like that, okay? That's an exclusive or. That's an exclusive. Do you like this thing or do you like this thing? Okay. I could ask the exact same question, same words, emphasize the wording a little bit different. I can say, do you like chocolate or vanilla ice cream? And then your answer would be yes. Or maybe it's no. But so in that case, that's an inclusive or, okay? And you know, when we write it down, sometimes it's not clear. But in probability, whenever you see it inside this thing, it's always the inclusive. It's the and or scenario. So when we say, do you like chocolate or vanilla ice cream? It means, do you like chocolate and or vanilla ice cream? Okay. So this is always an inclusive or. So the rule for the probability of A or B, meaning and or B, is equal to the probability of A plus the probability of B minus the overlap, A and B. All right, let me draw a little Venn diagram here. Okay, so this circle can represent A. This circle can represent B. And what we want when we talk about A or B, let me color this in. Oops. I want this. Okay. The probability of A or B, this is kind of our whatever this shape is, okay? It's this plus the entire circle for B. But if I do this, then I've double counted this overlap. So I have to subtract off the overlap piece, right? So when I color this in, it looks like this. Okay, and so in order to get kind of the double circle part, we can take the entire circle of A, add the entire circle for B, but then we have to subtract off the overlap because we've double counted this. Okay. I mean, another method is to just add up the pieces individually. Okay. We could do this plus this plus this. This is another possibility. This is A and not B. This is A and B. And this is B and not A. That's also possible. Oh no. It's like all right, so let's try this out with an example here. Okay, so let's say we'll say some people wear glasses. We'll say we'll split the world into those who wear glasses and those who don't. Okay, and I don't know, I'm making up a number. We'll say 30% of people wear glasses. I don't know. And then we'll say some people are left-handed, okay? And just for simplicity, I'll do probability of left-handed is 0.1, okay? And then we'll say the probability that someone is both wears glasses and left-handed. I'm just going to write glasses and left-handed. Just for simplicity, I'll put 0.03, okay? So what if I say, what's the probability someone wears glasses or is left-handed? Okay, this being the and or, the inclusive or. Okay, well this would be, so the rule before was probability of A or B is equal to the probability of A plus the probability of B minus the overlap, probability of A and B. You know what? I realize I haven't done a clicker question. I think we're going to run out of time to do a real question, so this will just be an attendance point, okay, today. Okay, something's wrong with my computer actually, and it's not. What's going on here? Hi. Sad. Oh, look at this. The shortcut is broken. Oh man. Restore previous versions. Okay. All right. I don't know. I don't know what happened. Tisk tisk computer. Okay. Well, maybe this will work. I hope. Okay. So anyway, let me just continue on. This is probability of glasses plus probability of left-handed minus the overlap, probability of glasses and left-handed. So this will be 0.3 plus 0.1 minus 0.03, 0.37. Computers revolting against me. Okay. Let me show you what else we can do. We can also make a table if we want to answer some tougher questions. Okay. So I'm going to make this the kind of the total column and the total column or total row. All right. So we can say glasses and versus not glasses. And then I'm just going to write left-handed and then not left-handed. Okay. So the glasses in the total, we're going to put what? 0.3, which means not glasses will have 0.7, right? Okay. And then what goes here for left-handed total? 0.1, and that means not left-handed total goes 0.9, and so here my total is 1.0. Okay, what value goes here? 0.03, right? Glasses and left-handed, 0.03. And once I plug this in, I can figure out the rest, right? I know that these two things have to add up to 1, so this has to be 0.07. These two things have to add up to that, so this has to be 0.27. And these have to add up, and these have to add up, so I get 0.63. Yeah? Okay, and then so now we can answer questions like, what is the probability that someone has glasses and is not left-handed? Okay, and what would our answer there be? Okay, so this would be probability of glasses and not left-handed, 0.27. Okay, I think the clicker thing started. All right, just click A. All right, and then we'll give everybody a point here for being here, having your clicker. Good job. You guys get a star. Okay, so click in A. Wow, everybody, somebody clicked B. All right, did everyone get their clicks in? That's like a record time. Okay, well, good job, all 156 of you. So we'll hit stop here. Okay, so you guys get this point. All right, so we can do this. Oh, we're not done. We're not done. Don't pack up and leave just because the attendance was taken. All right. Another way. Let me go back to this question. Probability of glasses or left-handed. Again, we can also answer it by kind of picking these pieces, right? There are three things that qualify as glasses or left-handed. We have glasses and not left-handed, plus glasses and left-handed, and not glasses and left-handed. Okay, these three pieces, if I add these three together, I will also get 0.37. Okay, so if we flip back to this, you know, one way was to do 0.3 plus 0.1 minus 0.03. That was the way we calculated. But if we did A and not B, if we call A glasses and B left-handed, this is 0.27, this is 0.03, and this is 0.07. Okay, so these are kind of the different ways that it could work out. Okay, so this is what we have here. All right, is that okay? All right, and then another possibility is instead of having probabilities given to you, okay, the information can also be presented as counts. And then it's the same thing. Information might be presented as counts, and then you just have to do a little bit of division. Okay, so we could say, I don't know, what are our options? We'll say people can have a cat or no cat, and then we'll say they have a dog or no dog. Okay, these are, and then so if I say I don't know, I'm just making up some numbers. 70 people have cats and 170 have no cats, and 80 people have dogs, and what is it? 70 plus 170 adds up to what? 240. So that means 160, and then 80 and 70. I'm just going to put in 45. So this means I can't add 35, 45, and 25, and this is 135. There we go. Okay, good job, me. Okay, and then so we can ask, you know, what is the probability someone has a cat? All right, okay, we'll say I pick a person from this table at random, right? A person from the table at random, meaning everybody at the table, person from the table at random. Okay, what is the probability that someone has a cat? And you would say, oh, that's 70 divided by 240. So probability of cat is this. Okay. And then I could also ask, I pick a random person. What is the probability that the person has a cat or dog? So probability of cat or dog. This would be probability of cat plus probability of dog minus probability of cat and dog. All right, cats, 70 over 240. Dog, 80 divided by 240. I'm not doing this too quickly, am I? Okay, and then cat and dog minus the overlap, 45 divided by 240. And these all have a common denominator, so we just add these up, and we get 105 divided by 240. All right. This is going to be probability of cat or dog. Now, if we look at what we're doing, when I say 70, probability of cat is 70, that 70 is made up of these two numbers, 45 and 25. Those two together make 70. And when I talk about this number 80 is made up of these two numbers, 35 and 45. So we can see that if I'm adding those numbers up, 70 and 80, I have double counted the 45, and that's why I need to subtract it off. Okay. Alternatively, I could just do 25 plus 45 plus 35. Okay. So another way is just to do 25 plus 45 plus 35. Okay. All of these things divided by 240. This would also give me 105 over 240. Okay, we'll end here for today, and we'll see you guys on Wednesday.